Welcome back. In this lecture, we're going to talk about the correlation coefficient, more specifically the Karl Pearson's coefficient of correlation. So, a little background on correlation before we get into the formula, etc. The Karl Pearson's coefficient of correlation is tests the measure or the strength of linear dependence between the two variables. To test the linear independence between the two variables need to be continuous or ratio variables. So they cannot be nominal variables, and while we can do it for ordinal variables, it's not recommended. So the Karl Pearson's coefficient of correlation recommends that we do it for two continuous variables itself, for example, like age and height, or age and weight. But we cannot do the correlation between age and name or age and gender as such. So it measures the strength of linear dependence between two variables, and it returns a value, a numeric number. So this is not the p-value, or this is not a hypothesis test which returns a probability value. It returns a value which is completely different from the probability values. It returns the correlation coefficient value, which ranges from +1 to -1 inclusive. That means the correlation at a maximum can be +1. The minimum is around 0, and then we have the negative correlation. So we don't say a negative correlation is lesser than 0. So the strength of the correlation is measured as the modulus of the number. That is by ignoring the sign. The sign only tells us the direction of the relationship. So for example, if we get a correlation value which is close to 0, it implies a weak linear relationship between the two variables. If we get a value which is closer to +1 or -1, it implies a strong linear relationship. So what does the sign signify? The sign simply signifies the direction of the relationship. So the relationship is classified as either a direct relationship or a inverse relationship. So in a direct relationship where the sign is positive, it implies that as variable 1 increases, the other variable also starts to increase. A inverse relationship is a case where if one variable increases, the other variable's value goes down. A graphical representation would be something like this. So for example, if we have two variables, let's say x and y, and we have observations for these two variables. So each observation pair becomes x1, y1, x2, y2, x3, y3, all the way till xn and yn. Now these two variables could be measurements of, let's say, height and weight of the individuals. So we may have n individuals, and for each individual we've recorded the height and weight as x1 and y1 pairs. So we've got n number of observations. Now a direct relationship would imply that if I increase the height of the individual, the weight will also start to increase, or we will observe. So not start to increase, we will observe. So if I direct or if I convert this data set into a scatter diagram, where we have x plotted on the x-axis, we've got y variable plotted on the y-axis. So each of these observations, as we mentioned in our first lecture itself, becomes a point on the xy plane or on the two-dimensional plane. So this whole data set, if we translate it into a scatter diagram, so we'll have something like this. So each observation is essentially the value of x and y at that point. So let's say this observation over here translates into x3 and y3. So we've got x3 and y3 over here. I'll just remove this. So we get a scatter diagram. Now what the correlation essentially does is it looks at the scatter diagram, or it looks at the relationship that we can see between x and y, and it figures out what is the strength of the linear relationship. So in this particular diagram, we can see that as value of x increases, the value of y also increases, and it follows some kind of a linear relationship like this. Now the closer the scatter diagram is towards the line, the stronger will be the linear relationship. The further the scattered plot goes away from the line, the weaker is the linear relationship. So essentially what the correlation coefficient does is it checks how close or how strongly related is the scatter diagram to the hypothetical linear line addressing the relationship. So if the two variables are perfectly correlated, then the scatter diagram will be lying completely on this 45-degree line without a single point away from it. So more of these points, so the more the distance between these points, the more scattered is the scatter diagram, and in that case weaker is the correlationship. So if I have a very tight grouping around this line, then I have a correlationship which will start to approach +1. If I have a very weak scatter diagram, so the scatter diagram is essentially, let's say, all over the place, it isn't coming any close, or there in fact no line can be performed, or there is no linear relationship which can come out from here, so there's no line over here. In that case, the correlation value will start to approach 0. Now, if the shape of the line or the direction of this line is positive, that means the slope is positive. Therefore, if as x increases, I observe an increase in y in the data set. So that's a direct relationship, and we get a positive correlation. In case I have another data set, and if I plot it, well, let me just plot it into a new diagram. So let's say I have another data set x and y, and I start plotting the correlation coefficient or the scatter diagram, and I get a scatter diagram which looks something like this. So as I can see that there might be a linear relationship, and the line which is trying to capture the linear relationship is something like this. So even though these variables x and y, they are correlated, so there is a correlation. The scatter diagram seems to come in forming around a certain linear formula, but the direction is inverse. So as x increases, the value of y starts to decrease, or if y increases, the value of x starts to decrease. So this is an inverse relationship. In this case, the correlation will be high, but it will be negative. So the sign of the correlation, the sign, negative or positive, simply tells us whether the correlation is direct or inverse. The closer the value towards 1, the stronger the relationship. So it's the correlation coefficient is something like this. So let's say we have 0 over here, we have +1 over here, and we have -1 over here. So the closer the value towards 1 on both sides, plus or minus, the stronger the correlation value, or stronger is the strength of the linear relationship. The closer the correlation is towards 0, the weaker is the relationship between the two variables. So what we're going to do, the correlation essentially does is it takes two variables at a time, and the correlation is always between two continuous variables. So we can't calculate the correlation of three variables at one shot. So the correlation coefficient always captures the relationship between two continuous variables at a time, and based on the value of that correlation coefficient, we can determine the strength of the linear relationship. So how does the correlation formula work? So the correlation formula is nothing but the covariance of x and y. If the two variables for which we want to calculate the correlation, we simply take the covariance of x and y and divide it by the product of the standard deviation of x and y, and that will give us the correlation coefficient, which is given by rho. So this is known as rho for the population. So if we have the whole population, it's called rho. If we are working with samples, we call it small r. So in fact, since we are almost always working with the samples, so we always call it the sample correlation coefficient, or the small r. So I'm going to take a simple data set and demonstrate how do we actually calculate the correlation. So I'm going to use the HSB data set. Let's pick out two variables, read and write, and let's check out the correlation for these two variables. Since we're going to do it by hand on Excel first, let's take up only, let's say, 15 observations, and I'm going to delete the rest of the data. So we just want to talk about these two observations. The first step is that we need to calculate the numerator, which is xi minus x bar into yi minus y bar. So xi and yi are simply the summation of I is equal to 1 to n. That is, for each row that we have to calculate this. X bar and y bar are the means of the variables. So I calculate x minus x bar first. So I'm just going to call it x bar over here, and it is going to be x minus the average of read, and I'm going to lock the formula for average so I can drag it down. and there we get it. And now I'm going to calculate y minus y bar. Y variable over here is read, so I'm going to take y minus the average of y of the formula, and here we give it. So this is the x minus x bar and y minus y bar columns calculated, and we have to multiply this. So I will take up the numerator over here. Numerator is nothing but multiplication of these two columns. So we multiply it, and finally we have to add it up. So it is summation of xi minus x bar into yi minus y bar. So the final numerator is the summation of the whole column. So I just add it up. So we get the sum of the column, and there we have it. The numerator is 488. So let's calculate the denominator now. The denominator is xi minus x bar whole square under the root, or which is the standard deviation. So I simply take this particular variable, and I'll just take this variable and I will square it. So let's add the square term. So I'll call it squared to make the column clear. So we're going to take this and we're going to multiply it with itself. So we get a squared term. And similarly for y minus y bar, I'm going to calculate the squared term. This is equal to y minus y bar multiplied by itself, and there we have it. So now the formula says that it has to be summation of the squared term and then the under root. So we are just going to calculate over here is square root equal to square root of the summation of this column. Something went wrong with my formula. It's fine to me, so let's try it again. The square root of the summation. So I didn't put in the sum formula, I just passed a range into the formula. A rookie mistake. We all get distracted sometimes. Over here. And I'll do the same for the next column. And finally I have to multiply them both. So the denominator is simply the multiplication of these two terms, and there we get the denominator. So the correlation for R is calculated as numerator divided by denominator. So we get a correlation coefficient of about 0.42. So where does 0.42 lie? So if I look at my graph over here deciding the strength, anything close to 0 is weak. So it's coming around here over here. So 0.42. The first thing first is that it's a positive correlationship. That means the relationship is not the inverse, it's a direct relationship. So the relationship is actually following a line like this. So as math score increases, as the read score increases, we observe a increase in the write score as well. And the correlation is halfway between weak and strong. So it's neither weak nor is it extremely strong. It's somewhere halfway. So about medium strength correlation. And the way we've calculated this is 0.42. We can actually use an Excel formula I also built in. Excel has a Corel formula which will allow us to bypass all this all so much of typing. So I can simply use a formula which is Corel, and there we have it. Corel, pass it the first array, comma, pass it this next array. We need to make sure that the two arrays are absolutely equal to each other, because in correlation we are looking at each point. So each point is defined by the two variables that we have. So the number of observations in each variable has to be exactly the same, and they need to be paired. So the correlation is a paired statistic. By paired I mean these two arrays that we pass are not supposed to be independent samples. They're supposed to be paired samples, i.e. for the same observation we have a value for x, and for the same observation we have a value for y. And we look at it, and we get the exact same correlation over here. So No particular need to calculate the numerator and denominator separately. So this was done just to demonstrate how the formula works and how we implement it. But Excel has a built-in formula, so you just use it as equal to Corel and then calculate it. So let's look at the correlation for, let's say, if I want to look at the correlation for science and social studies. I look at science over here. I select social studies over here, the full array. Close the formula, press enter, and there we have it. The correlation between science and social studies is 0.465. So again, a medium strength correlation and positive in nature. So it's a direct relationship. Increase in one subject shows or demonstrates or displays an increase in the other subject as well. So this was basic correlation coefficient. I'm going to move on to how useful and where all do we use correlation. So correlation can be studied graphically as well as using coefficients. So the way to study the correlation graphically is primarily through scatter diagrams. So if I look at read and write, so if I want to generate the scatter diagram for this, I can go to insert, do a scatter, and there we have it. So this is the scatter diagram between read and write. And as you can see, so if I add a trend line over here, the normal linear trend line, we can see that the trend line is following a direct relationship. So increase in one variable gives us an increase in the other variable as well. So we've got one subject on the x-axis, the other subject on the y-axis, and we see a fairly strong clumping or a linear relationship around this line. So in case this clumping does not show any particular value or does not show any particular trend, in that case the correlation tends to be close to 0. So these are the simple scatter diagrams sourced from Wikipedia, which give an example of the strength of the relationship. So if I look over here, you can see what a scatter diagram with 0 correlation looks like. A positive 0.4 correlation, a negative 0.4 correlation. The positive 0.8 is extremely strongly correlated. So you can see 0.8 and minus 0.8 are direct and inverse mirror images of each other. And then we have a correlation of 1. So one particular one particular confusion around correlation which comes up pretty often is the slope of the linear relationship between the two. So we'll cover slope and basically what regression means. But in case some of you are aware of what slope means, the correlation is not a measure of the slope. Slope of the two variables have got nothing to do with each other. The linear relationship can follow any particular angle between x and y axis. So it could be a 45-degree line, it could be a 0-degree line, it could be a 120-degree line, a line which is on the negative side. So the line and the angle which the line intercepts the x or the y axis has got nothing to do with the strength of the correlation. So if you look at all of these particular lines, these are the correlations of value 1, and it doesn't matter what the line or what the slope is. The correlation is only a measure of how closely or how tight is the scatter diagram against this hypothetical line. If the complete scatter diagram lies on the line itself, it's a correlation of 1, and the slope of the line has no impact whatsoever. The other thing that we need to take into account is that the correlation is only a measure of the linear dependence. So if you look out here, it's only the linear dependence. In case x and y have a non-linear relationship, then the Karl Pearson's correlation cannot capture this. So in this third row over here, you can see that between x and y we have some pretty interesting shapes coming out. So there is a relationship between x and y, but the correlation is always coming out to be 0. So even in fact we've got a circular relationship, but the correlation is 0. Why is it 0? Because it's only measuring the linear interrelationship. So one particular or one very important fact that we must keep in mind is that if a correlation comes 0 or close to 0, it does not signify that there is no relationship between two variables. It only signifies there is no linear relationship between two variables. I'm going to show you an example of this. For example, let's take two variables. I've got x and I've got y. I'm going to generate x as a random variable. Let's generate this as a random variable, and I will generate let's say about 27, 28. Let's generate about 100 observations or so, and I'm going to make the other variable a perfect function of the x variable. Is simply going to be an exponent of x. I'm just going to lock this variable down, and I'm going to remove the formula. So Control C, replace by values, and we have this variable. So x and y. Now y is a perfect function of x. Therefore x and y have a very strong relationship with each other. But if I generate the scatter diagram for this, and you will see that the relationship is very close. So we get an exponential relationship over here, right? And the scatter diagram is perfectly lying on this exponential line. So if I should get a correlation value of 1, but if I do a correlation over here, I won't get a correlation of 1. I'll get a correlation which is less than 1, even though y is a perfect function of x. I get a correlation of 0.99, right, which says that there is a strong linear relationship, but it's trying to measure a linear relationship when there actually exists a exponential relationship. So if I change this from a random variable of between 0 and 1 to even bigger variable, this problem will get even more inflated. For example, I use the rand between function and generate a value between 0 and, let's say, 100, and I generate exponent based on this. Get a value of 0 to 100 and exponent of a over here. I've got a 0 and 1 over here. So let me remove this formula from 0 to 100. In fact, I'll just make it from 1 to 100 to get it in a better way. Alright, so here you can see that the correlation is actually degraded down to 0.24. So even when y is a perfect function of x, and as you can see the formula is still running, so y is a perfect function of x, the correlation is not able to capture it. The correlation says there's a very weak relationship between x and y. It shows that because the relationship between x and y is not fitting very clearly on a linear line. It actually falls on an exponential line. But the Karl Pearson's coefficient of correlation cannot capture this relationship. So in case if this was instead of exponent, it was a natural log, we'll still have the same problem. So we have a natural log coming in. So you can see it becomes almost an asymptote, but here the correlation value starts to fall down as well. And if I change this to, let's say, rand between 1 and 50, let's look at how the correlation fares. It starts to go down, and let's say rand between, let's say, 1 and 10. So you can see, so you can change, you can actually do these experiments on your own. So if you have a perfect circular function, also a exponential or a logarithmic, even though the relationship is perfect, the correlation will not be able to capture it. So that's what I wanted to signify over here. A correlation of 0 or a low correlation does not signify no relationship between the two variables. It only signifies no or a weak linear relationship between the two variables. One more thing that is a cause of concern is the relationship between correlation and causation. So there's a lot of confusion regarding correlation and causation. Just because two variables are correlated to each other does not imply that the two variables have a relationship that follows the cause and effect. So correlation does not imply a cause and effect relationship between one another. And I'll give you an example. For example, we have a data set of sales and advertisements, and we contain the sales and advertisement budget year on year for the last 15 years. So imagine a hypothetical data set where for each of the last of the 15 years we have the annual sales and the annual advertisement budget captured in an Excel sheet. Now, if I do the correlation analysis and if the sales and advertisement comes out correlated, can we say that sales and advertisement are highly correlated? So why don't we increase the advertisement for the next few years and the sales will also go up? So that is a case where we are implying a causation due to correlation, and that's not a very good idea. So just because sales and advertisement appear to be correlated does not mean changing one will impact the other. It could be. Now, the reason why they are coming correlated is it could be that in years of high sales, when the company is making lots of sales, it has lots of money on its hand. Therefore, it funds a higher advertisement budget. In the downturn, when the economy goes down, the sales of the company goes down. As a consequence, the company starts cutting the advertisement budget. So when I plot this on a scatter diagram, you would see, high sales, high advertisements, low sales, low advertisements. Ergo, if I want high sales, why don't I have a high advertisement budget? So it won't work that way. And that's a trap where many companies and many analysts get caught on. That if two variables are correlated, maybe if I change the value of one variable, going forward, I will be able to have an influence on the other variables. It doesn't work that way. There could be a third variable in the background which might actually be controlling both x and y. So a high correlation between x and y does not imply x to be a function of y or y to be a function of x. Both x and y could be functions of a third underlying variable which you may not be able to capture. It may not be even there in your data set. So again, a very strong argument is always reinforced whenever we do correlation analysis, that correlation does not imply causation in a data set or in between the two variables. Now, before we move on to doing correlation analysis using SAS or the other tools, we want to talk about a little bit about the drawbacks of the Karl Pearson's coefficient of correlation. So we've already covered correlation and causation. So I want to talk about the impact of outliers. To understand the impact of outliers, one must look at the formula once more. As you can see in the formula, we are using a squared term over here. We are multiplying the variance of x into the variance of y. And there's a multiplication factor involved over here. And what this does is that if there are outliers in my data set, it can actually inflate the correlation when there is none. I'll give you an example. Let's have two completely random variables x and y. And I'm going to plot this as well. So this is a completely random variable x, and let's have, say, 200 odd observations on x, and I'll do the same with y. So we'll create a random variable here as well, and there all the way, and just do a base special values. Now these are two variables which have been generated randomly. So if I look at the scatter diagram, I should see a random scatter. So and that's what I see, a random scatter. If I look at the correlation over here, I'll do the correl formula here. I should get a correlation which is close to 0. I do not expect a high correlation here. And as expected, you see a correlation of effectively 0.0. Right? The negative sign is insignificant in this case. We get a correlation of 0.0. There is no relationship between x and y. Now what I'm going to do is I'm going to introduce one outlier. So over here, if you see x and y, both of these two variables are ranging between 0 and 1. So there's no observation which is less than 0. There's no observation which is greater than 1. And this is true for both x and y. So as of now, we don't have an outlier in the data set. But I'm going to introduce one outlier over here. So I'm going to have an observation with value of x as 10 and y as 10. And what you will see is suddenly the scatter diagram gets compressed in one corner over here, and we have one outlier over here. And now you look at the correlation value. The correlation has suddenly jumped up from effectively 0 to 0.82, and 0.82 is considered a very high correlation. So if I do a correlation analysis now and I simply look at the correlation value, the analyst or the modeler will conclude, hey, x and y are very highly correlated variables. There's something here. Let's do some analysis over here. But it could be that this high correlation value is getting inflated due to presence of outliers. And this will get even more extreme if I introduce more outliers like 5 and 50 over here, 5 and 5 over here, and let's say 20 and 30 over here. Now this correlation starts that's jumping up. and you start getting a correlation which starts approaching 0.99 very quickly, and you will then start imagining that x and y are in fact perfect functions of each other. They're practically the same variable, but that's not the case. You just a couple of outliers, not even a couple, just even one outlier can completely turn the correlation analysis around. And this is a major weakness in the Karl Pearson's coefficient of correlation, that even one outlier can inflate the value of correlation. So the next question that arises is, how do we detect outliers? How do we make sure that, the outliers are not impacting it? To which I always say that one should never study correlation analysis in isolation. As a rule, I always generate the scatter diagram between the two variables for which I am doing the correlation analysis in depth. So you cannot go ahead with simply the correlation value. What the correlation analysis does, it gives us a fallacy that if I want to study the relationship between x and y, I can generate one number, which is the r value, and just look at that. So so while correlation is a very strong statistic, it is also a great temptation to, make a shortcut on the analysis. Why should I study x and y separately, or why should I look at the distributions? I just generate the correlation matrix and or the correlation value and look at that. That's a shortcut. It doesn't work very well, and you're bound to make mistakes. So what I would suggest is, whenever we do correlation analysis, we always generate the scatter plot. And the scatter plot doesn't need to be a very fancy scatter plot. You can do it on Excel as well, and then look at the correlation value. So never look at correlation in isolation. Always generate a scatter plot unless you know the data set does not contain any outliers. So the HSB2 data set, we know that all the scores of the students, read, write, math, science, social studies, are scaled towards a fixed scale, so they are unlikely to go beyond 100. And there are no specific outliers over here unless there is some data entry error. So in this case, you can skip, building a scatter diagram. But for data sets which you are not comfortable with, or you have not worked with before, you don't know the ranges, it's always better to do is look at the histogram of the variables individually, look at the box and whiskers plot, and most importantly, generating a scatter diagram. So once the scatter diagram comes in, it becomes very easy to look at whether they are outliers or not. So if there are no outliers, this is what it looks like, and you get a correlation value of basically 0 and 0. If there are outliers in your data set, even small, even one outlier, and the correlation suddenly jumps up to 0.5. So this was what we wanted to cover for the impact of outliers. And we've already demonstrated that it only measures the strength of a linear relationship. So it cannot test the strength of non-linear relationships. It can only be used on parametric variables. It cannot be used on non-parametric variables. So we can't test the correlation between two non-parametric variables. We use the chi-square test to check the relationship between two nominal variables to a certain extent. So a chi-square test, while it does not give the direction, etc., it cannot. It checks the independence or dependence of two variables. But if the two variables are continuous, then only a correlation value can be used. And what now I want to cover is a related correlation coefficient known as the Spearman's rank correlation. Now this is a related concept to the Karl Pearson's coefficient. The Spearman's correlation is a derivation of the Karl Pearson's formula itself. What the Spearman's correlation does is it removes the impact of magnitude from the variable. What it essentially does is it converts every data into ranks and then runs Karl Pearson's coefficient on the ranks. And I'll give you an example of how Spearman runs. For example, if we go back over here, I've got a data set where the observations are randomly chosen between 1 and let's say a million, and we get the y variable is simply the log of x. So we get a correlation of about 0.9, as you can see over here. So I'll just fix these formulas over here so they don't run, they don't change every time I change something. So I get a correlation of 0.90. What Spearman will do is it will not run the correlation directly on x and y. It will create a variable which is x ranks, and then it will create a variable which is y ranks. What it will do is it will change each value into the rank it holds in that particular column. So for example, what is the, if I sort column X by the values, at what is the row number, what is the rank of this particular observation. So if I change this into the ranks, I can simply use the ranks function in Excel. So it picks up this number and ranks it in a data set. So I'll select the full data set, I'll lock it, and let's say I want ascending order, and it converts it into rank. So a value of 65,000 essentially becomes a rank of 120, and I'll do the same with the Y as well. So we use the rank function here, select this, take the full reference, and same ascending over here as well, and change it into ranks. So what you have essentially here done is the value of X earlier was ranging from about 1400 all the way till 996,668. So, and now it ranges from value of rank 1 all the way to rank 191. So we've ranked the observation, and I now run a correlation between only the ranks, and I run a Karl Pearson's coefficient of correlation. So there's no other for different formula here. It's the same correlation formula, and I look at the correlation, and the correlation comes out to be, let's say, 0.68. So in this case, it's coming out to be 0.68. So this is the Spearman's correlation. So what it will do is it will convert both X and Y into ranks and then generate a correlation on this. So if I generate a scatter diagram for this, I see this is a scatter diagram. It is a positive correlation, and that's how we generate the correlation coefficient here. I'll just look at the way observations here. Yeah, I'll look at the rank. Everything is running here correctly. Just make sure the formula is fine. Yeah. So what we've done is, if we run the Karl Pearson's on rank, it will generate the Spearman's coefficient. So Spearman is nothing but Karl Pearson's on rank. There's no different formula. It's simply running on the ranks over here. So this is known as a non-parametric correlation, or a correlation which can run on ordinal variables. So there's some positives of running Spearman's rank correlation as well. So I'll come to that a little later. So before we do that, one particular discussion which can generate pages and pages and books is what is the weak correlation and what is a strong correlation. So we already know that correlation is going to range from -1 to +1 between two continuous variables. Values close to 0 imply no or a very weak correlation. Values close to -1 or +1 imply strong correlation, either direct or inverse. But at what point does it changes from weak to strong to or strong to medium to weak? So there are no particular rules which define any particular cutoffs as well. So some suggested ranges have been given in a variety of books. So I'm putting in some ranges over here, but again they are only guidelines. They do not imply or they're not written in stone. So these are not rules as such, simply or merely guidelines. So typically between -0.2 to 0.2, this is considered as weak or effectively no correlation. From 0.2 to 0.3, and this works on both sides of 0. So positive 0.2 to positive 0.3, and similarly negative 0.2 to negative 0.3. We can assume that the two variables have some weak correlations over here. From 0.3 to 0.5 on both sides, about weak to medium correlation. 0.5 to 0.7, medium to strong. And anything above 0.7 on both sides is considered a very strong correlation. So again, a caveat over here. These are only guidelines. They are not actual suggested or written in stone. So it ultimately depends on what is the business value that the correlation is implying. So i.e. the strength of the correlation is in the eye of the beholder, or more importantly, what the data analyst considers to be strong or weak. So in some cases, even a correlation of 0.2 can be considered as strong. In other cases, a correlation of 0.75 can be considered as weak. It all depends on the situation. So there's no sort of rule over here regarding that. But anything close to 0 is implied as 0 is a weak correlation. So moving on. So a few points on the Spearman correlation, where it will rank better than Pearson's. So for first thing, it is immune to outliers. So I'll give you an example over here. So in this case, the outlier, it's a presence of even one outlier can effectively jump up the correlation to an extreme value. So I have one outlier and it goes up to 0.95. If I remove the effect of this outlier, it jumps back to 0. So even one outlier can change the value of correlation. But what if I started running this correlation on only the ranks? So I create the variable again x ranks and y ranks, and let's generate the ranks for these observations. So rank this value in the whole data set, and similarly not rank the y value in the whole data set. And I'm going to run this all the way down. So this was Pearson's coefficient. Let's talk about Spearman's coefficient. So if I look at x ranks and y ranks and generate the scatter plot, I will see that the scatter plot does not have any outlier, because even the most extreme outlier can only be converted into a rank over here. So it takes an outlier can only take either the highest rank or the lowest rank. It will not move beyond that. And rank is again in the number of observations that we have. So if I now generate a correlation on the ranks, I will get a correlation which is pretty close to 0. So even though the Pearson's correlation running on the actual dataset gives me a very high correlation, Spearman is effectively 0. So if there is no outlier, both Pearson and Spearman are going to give us effectively 0 correlation. But if there's an outlier, let's say value of 50 and 50 over here, that's one outlier, and I get a Pearson's coefficient of almost 0.99, a perfect linear relationship. That's what Pearson is telling me, and that is all because of the presence of this one extreme outlier. There is practically no impact on Spearman. So Spearman's correlation coefficient is effectively immune to outliers. However, it does not test a linear relationship between the two variables. When I convert it into ranks, it removes, or it is not testing the strength of the linear relationship anymore. So Spearman is not testing the linear relationship between two variables. It's only testing the strength of monotonicity. So this is a very big word, monotonicity. What it essentially means is it is testing the direction of the relationship. That how strongly is the relationship either direct or inverse. By monotonicity, I'll try to draw it out. What does a monotonic relationship actually imply? A monotonic relationship implies that if I plot x and y together, x is here and y is here, as x increases, if y always continues to increase, so something like this. So even though this is an exponential relationship, this is not a linear relationship, this is a monotonic relationship because it has got only one direction. Similarly, this is also a monotonic relationship. It's a logarithmic relationship between x and y. Y correctly. As x increases, y also completely continues to increase. Now, if I draw a inverse relationship, something like this is also monotonic, that the direction remains the same throughout. As y increases, x continues to decrease. So this is a completely monotonic relationship. A similar variable like this, as x increases, y continues to decrease. This is also the case of a monotonic relationship because there's only one direction. Now I'll give you another example. Let's have a look at this variable. Something like this. Now this is a non-monotonic relationship because initially till this point, till this point, as x increases, y also increases. Beyond this point, as x increases, y starts to decrease. And again at this point, the direction of the variable changes. Now as x increases, y is increasing. So in between there are directional reversals. So this is a non-monotonic relationship. This is non-monotonic. So monotonic means one direction or mono. So this is a polytonic variable or a polytonic relationship. Poly means multiple. So we have a polytonic relationship over here, where the direction of the relationship between x and y starts to change depending on different values of x and y. So what Spearman does is it tests only the strength of monotonicity between the two relationships, i.e., is the direction remaining the same throughout or not. And the stronger the monotonicity, the higher is going to be the Spearman's coefficient. Obviously, departures from it will give us a lower relationship. So it can detect non-linear monotonic relationships easily. So it will be able to detect a hypothetically should be able to detect logarithmic or sigmoidal or exponential relationships easily, because those are non-linear relationships, but they are monotonic relationships. A relationship like a sine wave or a cos wave, where the sine wave effectively goes up and then goes down, etc. They will not be detected either by Spearman or by Karl Pearson. However, one drawback is that the correlation values tend to be subdued as compared to Pearson. So even if they may have a strong linear relationship, the Spearman value might come out lower than Karl Pearson's. The reason is obvious, because we are removing the actual magnitude of the variable. So if you look at the formula, the correlation formula, we are looking at x minus x bar into y minus y bar, where x and y can have extreme values. When I change this into ranks, the values of x and y, they go down drastically, and the bar, the x bar and y bar, simply becomes the median rank. So obviously the value of R goes down. So when we change it to Spearman's correlation, we tend to get more subdued values of R closer to 0 as compared to 1. However, that's not a rule always. So this was what we wanted to cover regarding the theory of Karl Pearson's coefficient of correlation. In our next lecture, we will cover the SAS syntax and do some correlation exercises, and also talk about generating the correlation matrix. So I'll see you in the next lecture on Karl Pearson's exercises.